Uh, Welcome to Knowledge Search channel. In this video, we will be discussing about MOSFET. That too specifically we will be discussing about MOSFET, which is called as Enhancement MOSFET. So MOSFET is nothing but a transistor. It's a type of transistor which is used in amplifier circuits, oscillator circuits, and almost all the electronic equipments or almost all the electronic circuits. MOSFET plays a very vital role in today's era for major applications, especially in VLSI circuits, RF circuits, and many other electronic circuits, okay, amplifiers, oscillators. MOSFETs are playing a very vital role. So, in this video, I will be demonstrating how this MOSFET is constructed, okay, then how it works and what are its characteristics and what are its differences between the earlier type of transistors like BJT, FET and other things, okay. So, I will be touching like that, and finally, we will be discussing about, we will be having a small comparison, and we will be closing with the characteristics, okay, what will be the characteristics. So, there are two type of characteristics, one is called as the drain characteristics, the other one is called as the transfer characteristics. So, we will be discussing both the drain and transfer characteristics, and we will be closing it, okay. So, this is how the entire video is planned actually. So, now let us go into the video, okay. So, here you can see that, okay, so this is nothing but this particular slide which is showing two different types of transistors. So, one is the BJT, the other one is the FET. What is FET? Field effect transistor. So, FET is nothing but, so this is the FET. So, MOSFET is nothing but it's a type of FET actually. So, before the invention of this FET, we were using this BJT. This BJT was the most used before the invention of FET. The main problem with the BJT is it occupies a little bit higher space. It is quite slower when compared to FET. Okay, so that is the main drawback, and because of which this BJT has been replaced with FET actually. But some of the advantages are like, BJT can be used in high power applications when compared to FET, because FET can be used only in the low power applications with high speed. So, wherever the speed is the main requirement and power is not a main constraint, we have to go with the FET. Wherever I am not bothered about the speed, but power is the main, okay, but that particular transistor has to withstand high power, then you have to go with BJT, okay. So, this is how we are using our transistors nowadays, okay. So, here you can see that, so this BJT is a current control device, whereas FET is a voltage control device. That is why it is very fast, okay. That is why, since it is a voltage control device, it is having high impedance also. The impedance is very high, whereas in BJT the input impedance, okay, that is the input impedance is very less. So, that is why it is called as a current control device, whereas this is called as a FET is called as a voltage controlled device. And also this FET, okay, this FET, it is having three different terminals, okay, that is one is called as a drain, source and gate, okay. Similar to your BJT, here also you are having three different terminals, that is drain, source and gate, okay. And you know that in case of BJT, the output current IC is controlled by the base current IB, okay. So, here you can see that there are three different terminals. So, one is called as a gate. So, here G is there. So, this is the gate. So, here you can see, so these are the three different terminals: gate, drain and source. Whereas, here you can see that in case of BJT, it is nothing but base, collector and emitter, okay. So, this is how it has been divided. So, here I have marked it as okay. So, here you can see that by controlling the VGS, okay, by controlling the VGS, I can control the drain current, okay. So, that is the drain current is output current in case of FET. Whereas, in case of BJT, I have to control the input current, that is the base current. So, I have to control the base current in order to control the output current. So, for example, if the base current is less, then the output current, our collector current also will be less. If the base current is higher, then the collector current will be proportionately made higher. So, this is how it works. So, it amplifies the current actually. Here you can see that based on the input voltage, the drain current can be varied accordingly. So, this is how it works actually, okay. So, this is how it works, okay. So you can see that I will say always say that FET is a having high input impedance. So it the main another one advantage is this FET, it requires very less space. Okay, it is very less. It can also so very less space, whereas it is here in case of BJT it requires more space. So why I am saying this is because that's why it is suitable for VLSI, that is small in terms of nanometer also you can manufacture this MOSFET, okay, FET or MOSFET or JFET or whatever may be. But whereas BJT is not suitable for VLSI circuit, so here it is not suitable for VLSI circuit because it cannot be manufactured in a very small one, okay, in terms of nanometer it's not possible, okay. So that's why BJT is not suitable for VLSI circuit, whereas MOSFET is suitable, okay. So how you classify? Okay, so now let's move on. So this is the basic difference between the BJT and MOSFET. So now we will move on. See here you can see that so now in this video we will be discussing only about the FET, okay, that is field effect transistor. The full form of FET is field effect transistor. So it is classified into two types. One is the JFET, so this is the older version, and MOSFET, which is the newer version. Again, JFET is again classified into two types, that is N channel JFET and P channel JFET. Whereas MOSFET is classified into two types, that is again here also the MOSFET, you can say depletion MOSFET and enhancement MOSFET. And again in enhancement MOSFET there are two types, okay. One is the N channel, okay, N channel. The next one is P channel. So two different types are there. So we will be discussing the main in this slide we will be discussing only about this enhancement MOSFET, because this enhancement MOSFET plays a very vital role in today's all the VLSI circuits and everything, okay. So so directly we will be going into the enhancement MOSFET, okay. We are not going to discuss about depletion MOSFET or P channel MOSFET, JFET or N channel JFET or something like that. Directly we will be discussing about the enhancement MOSFET, okay. So as previously discussed, E MOSFET is again classified into two types, that is N channel type and P channel type, and both the types are most frequently used in many of the circuits, and slightly different characteristics are there, okay. In few applications, N channel MOSFET will be more suitable, in some of the few applications P channel MOSFET will be the best option. So only based on its characteristics we can decide which type of MOSFET, enhancement MOSFET will be useful, whether enhancement or P channel, or sorry, whether it is N channel or P channel or something like that. So going into the construction, okay. So this is how the MOSFET is being constructed. Just a minute, okay. So this is just a minute, how this MOSFET is being constructed. So first, before going into the topic, I just want to convey what will be the full form of MOSFET. So you know what is the full form of FET, that is field effect transistor. But what is the full form of MOSFET? MOSFET is nothing but metal oxide semiconductor field effect transistor. Is it okay? So the MOSFET full form, okay. This MOSFET is having the full form as, let us see, this metal oxide field effect transistor. This is called as metal oxide semiconductor, okay. Semiconductor field effect transistor. So this MOS. So this is called as MOS. FET is nothing but FET, that is field effect transistor. So MOSFET, metal oxide semiconductor. So because we will be using some metal and also some oxide is used. Oxide in the sense SiO2 is used, silicon dioxide is used here, okay. So which really changes its property. So that's why it is called as metal oxide, okay. So since silicon dioxide is used in manufacturing this MOSFET, it is called as metal oxide semiconductor FET, and SiO2 is the one which is going to be used, okay. And so these are all the things which I have already I just want to wrap up again, okay. So the MOSFET, again it is having two different types. One is the depletion MOSFET and enhancement MOSFET. So depletion MOSFET is also outdated nowadays. Only the enhancement MOSFET is the one which is used most frequently. So enhancement MOSFET, it is used as switch in many of the applications, okay. In most of the digital circuits you can see this enhancement MOSFET, okay. and also in VLSI circuits, okay, and also in manufacturing the gates, NOT gate, AND gate, flip flops. I don't know about flip flops, but about gates, okay. I'm sure this MOSFET is enhancement MOSFET is frequently used. As well, nowadays it is also used in regulated DC power supplies, okay. So power supplies also they are using, as well switching high current switching applications also this is mostly used in inverters, okay. So now normally we use UPS, in that also we are using this MOSFET, and amplifiers we use, and also the main application is in the form of VLSI, okay. So VLSI MOSFET is the one most frequently used, okay. So now we will discuss about what is that enhancement MOSFET, how it works, what are the how it has been constructed, okay, and then we will go into the characteristics, and then we will close it, okay. So first we will be discussing about the next, that is you can see that two different types are there, as I have already told. One is a N channel enhancement MOSFET, the other one is the P channel enhancement MOSFET. So both are there. So here you can see that, so this is nothing but the N channel enhancement MOSFET, and this is nothing but the P channel enhancement. So it is very simple to identify. So here you can see, okay, so here you can see that P are used, that's why it is called as P channel. Here you can see N is used, so that's why it is called as N channel. So this is called as a P substrate, okay. So it is having a substrate is there, P substrate is there, and here you can see the two different highly, that is the N regions are diffused into that P substrate, okay. First that's how it has been constructed, and also you can see that the source and drain, okay, the source and drain are being taken out. So here you can see that for example this is the, so here this N is being diffused, okay, and here also this N is being diffused into the P substrate, and from this you can see that in from one N they are taking this drain, and from the other N they are going to take this source, okay. So this is how it has been constructed, okay. So this is how it has been constructed. So construction is very, very simple to understand, and you can see that there is a channel. So this is called as channel. So there is some region, in this region, this is called as channel. So there is no channel actually. So here you can see that in both the cases there is no channel. That's why it is called as enhancement. Why the enhancement means I just want to grow it. The channel will be built up. So that's why it is called as enhancement MOSFET. Okay, the channel will be built up. Okay. So so this is how it works. Okay. So I just clear the screen, and okay. So here let's go on. As we have already discussed about the construction, so again a small thing is there I just want to convey out over here, that is there will be an SiO2 layer, okay, which is there in order to prevent. So this is the SiO2 layer. So this SiO2 layer is there. So this grey colored region is there, no? So this grey colored region. So this is called as the SiO2 layer. So it is there, okay, between the P substrate and the this drain and source terminal. So this is very important. So this SiO2 plays a very vital role in shaping the characteristics of the MOSFET. Okay. So without this SiO2 region, it is it will not behave like this. So SiO2 layer plays a very vital role. It is going to just isolate the gate from the region between the drain and source. Okay. So this is how it looks like. Okay. This is called as the N channel, and P channel is there. So both N channel and P channel are there. Okay. So since there is no physical channel, so I have to grow the channel. So that's why it is called as enhancement. Okay. And you can see that both P channel and N channel are almost similar. Okay. Only thing is here I am using the P type substrate and N doped region here, whereas here I am using N type substrate and P doped region here. So this decides the type. This one decides the type. If you are having P, it is called as P channel. So here the channel formed will be in form of P. If you are having N here, then it is called as the N channel. Okay. So this is how it looks like. Okay. So now just a minute, I will just delete this markings. Okay. So this is how I just want to convey to you. And so now let us go into the operation, how it works. Okay, now let us go into the operation, how it works. So I will just discuss, I will just give you an idea of how this particular N channel MOSFET is working actually. Okay, so in order to make it work, we have to give two different sources. One is called as the VDS, which is nothing but it is between the drain and source. So here drain is there and here source is there. Between drain and source I have to give. Okay, this center, this thing is called as a gate, and this is the gate to source voltage and this is the drain to source voltage. So two different voltage sources are given. One is between the gate and source, the other one is between the drain and source. Okay, so this is how this particular MOSFET will be working. So since the gate voltage is positive, here you can see that the positive things will be there. Okay, the positive ions will be formed over here, and this will be attracting the negative electrons from this N doped region. From this both N doped region, it will be attracting the N, and because of it, the channel will be growing. Okay, so initially this channel was not there. So as you increase the VGS, you can see that the number of electrons will be attracted more, and there will be a particular voltage which is called as a threshold voltage, beyond which only this channel will be developed, and so that there will be a connection between N these two N regions, and because of it the drain the current from drain will be flowing through this channel to the source. So once the gate voltage, that is when once the VGS is greater than threshold voltage, you can see that, okay, you can see that VDS that is ID that is the channel will be there, and because of which the VDS current will produce a current, VDS voltage will be producing a current ID which will be flowing through this channel. So this is how it works actually. Okay, so if VGS is not there, if VGS is 0, if VGS is 0, then you can see that this nothing will be there in this channel, so it will not work. Okay, so since the VGS will be greater than the threshold voltage, then the electrons will be built up over here and the channel will be built out over here, and because of which the drain current starts flowing, and that drain current magnitude will be depending upon the magnitude of the VDS. Okay, so this is how it operates. Okay, hope you are all clear the operation, and similarly the same case will be for the P channel as well. Okay, so P channel, so the only difference is in case of P channel, see for N channel always you will be giving the positive voltage. For N channel the VGS should be positive, whereas P channel the VGS should be negative. This is very very important. Okay, only if we give the negative voltage, here the positive ions will be attracted, and because of which channel will be formed. So for P channel MOSFET I have to use negative gate voltage in order to work, whereas for N channel MOSFET I have to use the positive voltage. So this is a very important thing which I want to remember. If this is not followed, then your MOSFET will not work. Okay. So now let us go into the different symbols. Okay, so this is the earlier symbol. Conventional method is the older way of, so since this is the older way of marking the symbol. So here you can see that for N channel the pointer is inside. You can see that the pointer is inside for both, whereas for P channel the pointer is outside. But in latest version, okay, this is the latest version. So instead of using this complex symbol, nowadays we use this latest version. Here you can see that the middle thing is not there, whereas in the last one, so 3 lines are there here, whereas here only 2 lines are there. Okay, in latest version, and here you can see that for N channel it is facing outside, whereas for P channel it is facing inside. Okay, so this is what we want to remember. So symbols might be asked, so draw the symbol of P channel MOSFET and draw the symbol of N channel MOSFET. So you should be quite clear of how to draw it. So now let us go into the characteristics. Okay, so this is the characteristics of N channel MOSFET. Okay, so so you can see that there are 2 different characteristics. So one is called as a so this one, so this is called as a drain characteristics. Okay, this is called as a drain characteristics, and this is called as a transfer characteristics. Okay, transfer characteristics. Okay, so transfer characteristics is nothing but I am just going to plot the ID versus VGS. Okay, ID. So this is the drain current for different values of VDS. Okay, for example, I will be keeping VDS at particular value, and I will be changing this VDS, and I will be noting down what is ID. So this is how it goes. Okay. So similarly for drain characteristics, it is very simple. It is nothing but I V VDS, okay, ID was VGS, whereas VGS I will be having different sets of VGS. Maintaining VGS as a constant, okay, and I will be varying this VDS and noting down the corresponding ID. So here you can see that the plot will be looking something similar to this. So why we are getting something like this is because of that particular channel. So only when the threshold voltage is reached, you can see that only when the threshold voltage is reached, this current, ID current starts rising. So that's why the characteristics is like this. Similarly here you can, the same thing can be observed in drain characteristics also. Only, so until this one you can see that the drain current is quite small, but only when the threshold voltage is reached, you can see that the drain current has been saturated, because the channel width has been saturated. You can see that as VGS is increased, okay, as VGS is increased, ID saturation is also increasing. ID saturation is also increasing. See here for VGS of 4 volt, it is saturating at 1 amps, whereas VGS of 6 volts, you can see that ID is saturating at somewhere around 4 amps. Similarly for VGS around 8 volt, it is saturating at, it means that your channel width is getting increased because of higher gate voltages. Okay. Because of higher gate voltages, the channel width is getting increased, and because of the drain current saturation level is also getting increased. So this is what all about your characteristics. Okay, so this is what is all about your characteristics. Okay, and you can see that there are 3 different regions here. So this is very important. In case of drain characteristics, you are having 3 different regions. One is called as the cutoff regions. I will just mark it in a different color. Okay, so that for better understanding. So you are having a cutoff region is there. So here this cutoff region is nothing but when VGS is less than 0. Okay, this is VGS is less than 0, then that is called as a cutoff region. See here you can see next is saturation region is there, and next is ohmic region is there. So whenever VGS, okay, is greater than VDS, then it will behave in ohmic region. Whereas when VDS is greater than, okay, when VDS is greater than VGS, it will get saturated. So you can see that the drain current is getting saturated. Okay. So but you can see that as the VGS voltage is increasing, the higher level of saturation is there. So this is what is the final conclusion is all about the enhancement MOSFET, that is N-channel enhancement MOSFET. Okay. So different applications use this particular regions. Okay, in some of the applications they will be using in saturation, MOSFET will be used in saturation region. Some of the applications they will be using in ohmic region. Some of the applications they will be using also in cutoff region. Some of the they will be using only cutoff and ohmic region. Some of the applications they will be using in the saturation region. So depending on application, which type of region we can use this particular MOSFET has to be decided. So this is the characteristics. So next we will move on with the P channel. Okay, so P channel. So here you can see this is the P channel MOSFET. As I have already told, for P channel MOSFET, this VGS should be negative. P channel MOSFET. Whereas for N channel MOSFET, it's okay. N channel MOSFET, the VGS should be positive. For P channel MOSFET, in order to properly work, the VGS should be negative. So here you can see that VGS is minus 3 volt, minus 4 volt, minus 5 volt, and minus 6 volts. So similar to the previous one, as I increase the VGS voltage to a higher voltage, okay, that is where as the VGS is higher and higher, you can see that IDS, that is the IDS is nothing but it is also higher and higher. For example, for VGS of minus 3 volt, it is getting saturated at some 0.5 amps. Of VGS about minus 4 volts, it is getting saturated somewhere around some 2 amps. Similarly, VGS of around 6 volt, you can see that it is saturating around 8 amps, 8 milliamps. Okay. So this again here also you are having 3 different regions. One is called as the cutoff region. So cutoff region is nothing but when VGS is less than 0, it will be operating in the cutoff region. And similarly here, if VDS is greater than VGS, it will be operating in the saturation region. If VGS is greater than VDS, then it will be operating in the ohmic region. So this will be operating in the saturation region. So this is what you want to observe. So again in transfer characteristics, so since the VGS voltage is negative, so it has been plotted on the that is your second quadrant. So here you can see that this is your threshold voltage Vt. So until the threshold voltage, the channel will not be built. So only after that the channel will be built, and it will be the voltage will be, and this particular voltage is called as the pinch off voltage. Okay. So this is how it works. Okay. So P channel and N channel MOSFET, both the characteristics has been discussed. So now let us discuss about the difference between the depletion and enhancement. So now we have discussed only about the enhancement type of MOSFET. Okay, enhancement type is most frequently used, but I just want to convey. So in some of the question papers they will be asking what is the difference between the depletion type and enhancement type. So you can see that symbols. So here in case of enhancement type, it is in dotted form. You can see that here it is in dotted forms. Please observe very closely, it will be in dotted forms, whereas here it will be in straight line. Okay, so this is the symbol wise, they just differentiate, like putting a straight line for depletion type, whereas putting a dotted lines for the enhancement type. So here you can see that in case of depletion type, the channel will be there, but whereas it will be depleted, but whereas here the channel is not there. Okay, there is no channel, and it will be physically we have to build it. Okay. So similarly, the operation is there are two modes actually. In case of depletion MOSFET, there are two modes. One is the depletion mode, and the other one is the enhancement mode. Whereas in case of enhancement type, you will be having only one mode, that is the enhancement mode. Similarly, here the current flow. Okay, based on the current flow, the drain current will be flowing on application of the drain to source voltage. Even at VGS equal to 0, there will be small current flow will be there. Whereas in case of enhancement MOSFET, if VGS is 0, there will be no current. If VGS is 0, the drain current will be 0. Okay, if VGS is 0, the drain current is 0. So this is very, very important in case of this. So they will be asking this. Okay, this has been asked in many of the question papers, like what is the difference between enhancement and depletion type. So symbol wise there is a difference, something like this. So in case of depletion type, the channel will be existing, that is the existing channel will be depleted, that's why it is called as depletion type. Whereas in case of enhancement, there will be no channel, and that channel will be built up as you increase the VGS voltage. And operation, there are two modes of operation in case of depletion type. One is called as a depletion mode, the other one is called as the enhancement mode. Whereas in case of enhancement mode, you are having only one mode, that is called as the enhancement mode. Okay. Similarly, the current flow, in case of depletion mode, even with the VGS equal to 0, there will be a small current flow will be there. Whereas in case of enhancement mode, when VGS is equal to 0, drain current will be equal to 0. That's all about the enhancement MOSFET. I hope you're all clear with the concepts of working, construction, characteristics of the enhancement MOSFET, symbols, everything has been discussed in this video. So I'm sure this video will be very helpful for those who are preparing for MOSFET. Okay, and thank you very much for your patient listening. If you really like this video, give a thumbs up. As well, if you have any doubts, you can just comment. And if you feel that this particular video will be helpful to someone, you can just share it. As well, if you feel that if this particular channel and whatever videos I am putting, it will be helpful for you, you can just subscribe. And thank you.